Good morning to everybody present here. On behalf of ISI Bangalore students, I welcome all of you to the second day of Lib Camp 2025. Today's lecture will be given by Ruchira Mukherjee. She recently completed BMath honors this year. Her topics of interest are number theory and representation theory. I welcome her to speak on the topic modular forms and the four-square theorem. Please post any doubts you have in the chat. They will be addressed at the end of the presentation. Over to you, Ruchira. Ruchira, you are muted.
Oh, right. Okay. So everyone can see my screen? Hello. Uh,
Yeah, it's visible.
okay. Cool. So this will just be an introduction to the topic. I won't go into proof details too much because they are just basically mostly calculations. And if you find it difficult to understand me at any point, like I have the habit of going really low in my voice volume, so please feel free to say that you can't understand me or can't hear me or anything in between the talk and interrupt me. And yeah, let's get started. For this talk, I need everyone to have some prerequisites like basic complex analysis because I will be at least the definition of holomorphicity and meromorphicity. Like holomorphicity is like it's differentiable and stuff, and meromorphicity is like it can be written as a ratio of two holomorphic functions at least. Some group theory and basic topology, like the definition of manifold, like it is locally Rn. So for every open neighborhood of something, we have to define a map that goes to an open neighborhood of Rn, homeomorphism, yes. And those homeomorphisms are called charts. And compact Riemann surfaces, yeah. Basically, the definitions would be fine. So we define a group action on the Poincare upper half plane H. That is the set of all complex numbers with imaginary part greater than 0. And the group acting would be SL2Z. I mean, we can also do SL2R and stuff, but yeah, for motivating modular forms, I'll pick SL2Z. And we act like this. And the action gives me an element of H itself, because if the imaginary part of Z is greater than 0, then by this simple calculation, we get that imaginary part of AZ plus B by CZ plus Z would also be greater than 0. And this is actually a bona fide group action because it respects composition. This is a calculation you can check for yourself. But this is not quite faithful. Anyone in the audience, why is it not faithful? Hello? Like the group action is not faithful. What does it mean for a group action to be faithful? Can people hear me?
Yeah, you're audible.
Oh, okay. So let me see the comments if there. The thing is, I cannot check the comments while giving a talk. So, okay, so basically, a group action being faithful means there is one more element other than the identity element that acts on it the way the identity element does. Like there is one more element that acts trivially on the upper half plane, because minus I acts trivially as well. Because basically AZ plus B and CZ plus D, the ratio gets cancelled if we do that, right? So if we want to work with a group having a faithful action, we can pass on to this PSL2Z, which is just SL2Z quotiented by the plus minus identity. And the action is transitive because we can have, okay, the action of SL2R on the upper half plane is transitive. I made a mistake in here because x, like y to the power half might not always be in Z. Okay. So discontinuous action, the definition being that if gamma is a subgroup of G, we say that the action of gamma on H is discontinuous if for any two compact sets, K1 and K2, in the upper half plane, the set of gamma such that intersection is non-empty is finite. And the group SL to Z acts discontinuously on the upper half plane. This is also proven by some calculations, like some bounds on the entries of the matrix gamma, and finally showing that, like, for example, it can be proved actually that SL to Z is, that's a bad pen. SL to Z can be generated by two matrices, 1, 1, 0, 1, and 0, minus 1, 1, 0. So this acts as a translation kind of, like, not translation, stepwise thing. Like if you compose this with itself, it will give you 1, 2, 0, 1, and so on to 1 and 0, 1, and so on. And this is kind of inversion along a circle. I'll come to the figure later where this will be more clear. So, right. Now, I want to define what is called a fundamental domain. So if gamma is any group that acts like, not any group, for a general definition, I would want gamma to be like the index. Okay, I'll come to the general definition later. Anyways, gamma here is SL to Z. Gamma acts on the upper half plane as was given by the action, defined by the action before. Fundamental domain for gamma is an open subset F of the upper half plane such that for every Z in the upper half plane, there exists a gamma in gamma such that gamma Z is in the closure F bar. And if there is any Z1, Z2 in F, gamma of Z1 is equal to Z2 means that Z1 is equal to Z2. This kind of gives us the orbit the orbit representatives of the action of gamma on the upper half plane. So for SL to Z, the fundamental domain would be this area region defined in here. This is also kind of calculative. So again, you have to take the matrices and see what all, like I said, that 1, 1, 0, 1 is kind of like going this side, and 0, minus 1, 1, 0 is kind of inverting along a circle. So the diagram I want to show you is this. So the fundamental domain is illustrated with this shaded region, and T is 1, 1, 0, 1. This just takes any element here to an element here, and so on to T square and so on. And S would take an element in here to an element in here. So these sections of the upper half plane kind of tells you what are the images of the fundamental domain under T and S. And to see this proof, there are two ways that Keith Conrad does it in his notes. The first one is kind of just blatant calculation with the fiddling with the entries of the matrices in SL2Z. And the other proof is seeing the group action of SL2Z on the upper half plane. I would prefer the second one better, but yeah. So I want to define what are cusps now. We know what our group actions are, right? Okay, I think there has been, yeah, okay, fine, cusps. So consider a Cayley transformation from upper half plane to the open unit disk given by this. Like you can intuitively see that upper half plane means it's farther away from minus I, like, yeah, so it's closer to I than it is to minus I. And so this kind of gives a feel to the map, I would say. And this always gives you a thing that's less than -1. Then note that under the Cayley transform, the projective reals is going to be U, the unit circle. Basically, the upper half plane is kind of like all the things in here, and what we would uh, think of the boundary of this set would be is the real axis over here and the point at infinity somewhere up there. So this is kind of how we would visualize the boundary of H. And note that this is invertible, like there's an inverse of it. Okay. So SL2 actually acts transitively on the projective rationals. A subgroup of finite index of SL2 can have only finitely many orbits on the set. An orbit of gamma in P1Q is called a cusp of gamma. So basically, while we are mapping this fundamental domain stuff over here, Cayley transform C, this is the figure we get, where the point at infinity would map to the point in here where it touches the boundary of the circle. And that would be when you plug in, when you kind of try to plug in infinity over here, like you can do so by just and this thing would give me 1 and the other one would give me, and then rationalize the denominator and take stuff to the imaginary part of z to infinity, because the real part is bounded between this thing. We will see that it maps to 1 over here, so 1 on the unit circle. So yeah, basically the figure should be rotated. This should be the axis. This is 1 and this is -1, and this is minus I and this is I. Compactification. So the measure dx dy by y square here, dx and dy are kind of like when we say z is equal to x plus iy, I mean the partial derivatives to be in terms of these x and y. So I'm saying that if we say gz is equal to x prime plus iy prime, then this would be the same as this. This is all I mean by saying that the measure this is invariant under the action of SL2Z, where G is in SL2Z. The volume of SL2Z quotiented by H is finite with respect to this invariant measure. This basically translates to finding the volume of the fundamental domain with respect to this measure here, like basically calculating as x goes from minus half to half, and then y would go from something else according to some value, say 1, yeah, 1 to infinity. You just integrate this thing. Yeah, and this would give you some kind of pi by 3 or something. Like this would give you a finite value. That's all I mean. Right. So topology on this is the quotient topology. By this, I mean the topology on this quotient space is just if SL2Z, we have this map. So any set is open here if its pre-image is open in here by the star canonical map. Right. And this can be compactified to a compact Riemann surface by adjoining a point for the cusp it has. This is intuitively clear, like SL2Z had one cusp, like the map where the like intuitively where this is touching the unit circle. And for other subgroups of SL2Z with finite index, we would see that there are more cusps actually. Like for some other subgroups, this map on the unit circle can look like something of this sort. So there's 3 cusps over here. This is the group gamma 2 acting on the upper half plane. And gamma 2 here is a subgroup of SL2Z. No, not a subgroup of SL2Z. Basically, SL2 kernel of the map. Sorry. Right. So you take this map, and the kernel of this map is gamma n. Where each entry we're taking a modulo n, capital N. So that would give me gamma 2. Okay. So we can prove this. This is a manifold by constructing charts around points. So to prove that this is a manifold, we will have to show that for every neighborhood of a point, there will be a homeomorphism from that open neighborhood to an open set in Rn. So those maps will be called charts. And to show this, we consider these maps pointwise. And certain points are treated differently than others. For example, Some elements in here are known as elliptic elements, some elements as parabolic, some as just hyperbolic. Like if the SL2Z elements have trace less than 2, then it would be elliptic. And these can be shown to have two fixed points in the projective complex plane, like not plane, line, P1C. If trace is equal to 2, then it's parabolic. This has a single fixed point in P1R. And if trace is greater than 2, then it's hyperbolic. This has two fixed points in P1R, but no other fixed points in P1C. This is can be easily verified by just taking the determinant of the quadratic form these define. But yeah, so the fixed points of elliptic elements would be called elliptic points, and the matrices like this would have finite order always. So anyways, we have a separate construction of charts for these special type of points. Generally speaking, like we need to have this fundamental domain here and some measure here, like for a general group acting on the upper half plane. And that group needs to be discrete, like discrete. Let's not get into that. Let's just say that the fundamental domain should have finite volume. And only then we can actually talk about compactification and stuff like that. Okay, so there are, as far as this talk goes, there are two ways to motivate what are fundamental, like what are modular forms. The first definition is kind of just this formula. This is where k is even non-negative integer. A modular form of weight k for the group SL2Z is a holomorphic function on H satisfying the identity this. For a general subgroup of SL2R, this would kind of be the same thing, but again, we need to have that subgroup to have finite volume, fundamental domain, and stuff like that. And this is holomorphic at the cusp infinity. Like SL2Z has just one cusp, like the fundamental domain would just intersect the projective complex numbers in one point. For other subgroups, it would have to be holomorphic at all the cusps. So gamma n, as I was saying, is elements of SL2Z such that A and D are 1 mod n and B and C are 0 mod n. And that's practically the kernel of this canonical map. Gamma 1 is taken to be SL2Z. A subgroup of SL2Z is called a congruent subgroup if it contains gamma n for some n. The space of all weight k modular forms of gamma 1 is denoted by mk gamma 1, and this is a finite dimensional vector space. There's also a nice property that these things over here, like these are defined by this formula, right? and they have to be holomorphic at a cusp. So if we consider the Fourier expansion, like if we consider minus infinity to infinity, this thing here, we will see that for a certain sufficiently large n, we would have an is equal to 0 for all n less than n because of this holomorphic thing over here. Oh, no, sorry. Not because of holomorphic thing. Like if this alone just satisfies this equation, then we have to have this property. And because we are demanding that the cusp, it's holomorphic at the cusp, infinity and stuff like that, it will have to be, if holomorphic condition is considered, then an has to be 0 for all n less than 0. And furthermore, if a0 is 0, like a0 need not be 0 here. If a0 is 0, we say that it's cuspidal at infinity, or it vanishes at infinity. These things form a subspace of mk gamma 1. And that subspace is usually written as sk gamma 1. This is the space of all cuspidal forms. And we have a nice inner product on this. Like this is a finite dimensional vector space with an inner product, and it's a Hilbert space. And that inner product is called the Peterson inner product. We don't need that for proving the sum of four squares theorem, but yeah, good to know. So we need to see a concrete example of what would be a modular form. And so for that, we construct what is known as an Eisenstein series. Assume k is an even integer greater than, where k is greater than or equal to 4. This condition is crucial because for k is equal to 2, we don't have any non-trivial modular forms. That can be easily checked. And also for k is equal to 0, that would just mean that these are called automorphic forms. And if we demand that these are holomorphic at the cusp infinity, that means these are holomorphic on a compact Riemann surface. And if it's holomorphic on a compact Riemann surface, that means it's actually the constant function. Like any meromorphic function on a constant Riemann surface, like compact Riemann surface, having no poles is automatically constant. So for 0 and 2, actually, we don't have any non-trivial element of mk gamma 1. Right. So for k greater than or equal to 2, we consider this a weird sum, but okay. And note to take here is like, this is, of course, absolutely convergent. You can try this by yourself by considering cases like when m is equal to 0 or m is not equal to 0 and so on and so forth. Like m can be 0, but n cannot be 0. This is also a modular form of weight k, like replace z by that thing over there, and you will get that cz plus d is coming out, and the other terms would just be permutation of the integers. That's also quite easy to find out. We compute its Fourier expansion to show that it's analytic at infinity. For this, we use the residue theorem. You can see some terms over here that will remind you of the Cauchy's theorem. And that is also quite easy to see if you know complex analysis. And these things over here is just collecting terms for collecting common terms for the coefficients of q to the power n. Q here is e to the power. I generally refer this element as q, and so this would just mean q to the power n. Collecting coefficients of q to the power n together, we get this. The modular forms where the constant term is 0 in its Fourier expansion are called cusp forms. We have defined this before. So for k greater than or equal to 4, the dimension of mk gamma 1 is equal to this plus 1, because we have produced a modular form which has non-zero constant term, and that is precisely this. And we know that all the terms in this direction would all be 0 because we demand holomorphicity at the cusp infinity. Right. So let gk be 1 by zeta k of ek. Like we are just taking this term to be 1 here. Like I will refer to gk in the pages to come, but it can be some other multiple of ek, but it would just be a constant term multiplied with ek. That would depend on k. So when I write gk, just take a constant multiple of the Eisenstein series. We can show that this thing happens, and right. This is a really strange function to come by at a first glance, but this has some really nice properties. First of all, the nice property would be that the coefficients are multiplicative, in the sense that if m and n are co-prime, then the coefficients of amn would be am times an. These are two less coefficients, so as to, like, I've written two less coefficients to see this clearly, but it is so. This is called the Ramanujan's discriminant function, yes. And this is a cusp form of weight 12. Basically, we are taking the cube of a weight 4 and square of a weight 6, so it would give me weight 12. This is a theorem without proof that I'm citing here, that we can actually find the dimension of everything, all the cusp forms, or even non-negative integers. For odd, it would clearly be like there would be dimension 0, like there would be no non-trivial modular forms, because you can easily check that if we require this condition, then we require this condition for all the generators of SL to Z. And so things would go bad if we take case odd. And yeah. And it is kind of, you can also show equivalently that if this is like satisfied for the generators of SL to Z, like if we have f of the one generator was 1, 1, 0, 1, so and 0, -1, 1, 0. If a function such as this is holomorphic at the cusp, like here in just infinity, yeah, that would actually give you a modular form for all SL to Z. Right. So, yeah, where was I? Cusp form is fine. Yeah. This proof is very involved, so I would generally not even try to motivate it here, but still, it's quite simply calculations, I would say. If you are really interested in a good proof, I would suggest you go through the proof of this as is in Sayre's book. The Sayre's book is a course in arithmetic, first course in arithmetic. What are modular forms motivation to? This part is practically from Sayre's book. Like a lattice is defined to be such and such. Like it is a subgroup of a finite dimensional real vector space V, verifying one of the following equivalent properties. This would be V by gamma. So gamma is discrete, like I was trying to say that gamma should be discrete and this should be compact. Gamma is discrete and generates the real vector space V. There exists an R basis of V, which is a Z basis of gamma. So let this script R be the set of lattices of C considered as an R vector space, like C is kind of R plus Ri. So let M be the set of pairs W1, W2 of elements such that of C star, such that the imaginary part of W1 done by W2 is greater than 0. And to each such pair, we associate the lattice spanned by the basis W1, W2. We thus obtain a map M to R, which is clearly surjective. Like basically, for any lattice of C, we would have a basis. And we can just take W1 by W2 or W2 by W1. One of them has to have imaginary part greater than 0. So this is clearly surjective. And now if we take an element in SL2Z and let W1, W2 be an M such that imaginary part of W1 by W2 is greater than 0. And W1 dash is equal to this and W2 dash is equal to this. Then, oh, I think I've missed the dash. W1 dash and W2 dash is also a basis of this. And if we set Z is equal to W1 by W2 and Z dash is equal to W1 dash by W2 dash, we get that this thing happens. Where G is this and the action is defined as was defined. This clearly shows that imaginary part of Z prime would be greater than 0. And yeah, the fact that this belongs to M. For any two elements of M to define the same lattice, it is necessary and sufficient that they are congruent modulo SL2Z. We proved one direction and the other direction is left as an exercise. So we can identify the set of lattices of C with the quotient M by SL2Z. Now we define C star acting on R. This would be, and respectively on M. This will not be the real numbers. This will be the set of lattices. Oh, sorry. By this, so basically W1 comma W2, this basis set is set to gamma W1 comma gamma W2. This is the lattice we are taking. The quotient M by C star is identified with H by this. This identification transforms the action of SL2Z on M to that of SL2Z, quotient in blood plus minus I, PSL2Z. So thus we have proved the following theorem, that the map this gives by passing to the quotient of bijection of this onto this. An element of this can be identified with the lattice of C defined up to homothety. Homothety is like multiplying by a scalar. Right, so another paragraph to see. Let f be a function on the set of lattices R with complex values, and let k be in Z. We say that f is of weight 2k. Here, Serre just says that it's weight 2k instead of assuming k to be even and so on. If for all lattices gamma and all lambda in C star, we have that okay, so there's a printing mistake over here. This is the same line repeated again. We have that this thing happens. So if W1 comma W2 is in M, we denote by this the value of F on the lattice, lattice generated by W1 and W2. The previous line translates to this thing, like this line. Moreover, this is invariant by the action of SL2Z on M. Can you see the invariance? Yeah, of course, because this just takes the ratio. So SL to Z would just be AZ plus B by CZ plus D. So the ratios of W1 and W2, they would get cancelled. And so this shows that the product, this depends only on Z is equal to W1 by W2. That is because like just take W1 with the W2 and take oh, right. So this has a mistake. There will be no lambda here. We're taking the lambda out. Multiply by omega, like W2 to the power k. So this is why it remains invariant. This thing here is the same thing as this. And depends only on the ratio. So there exists a function small f on H such that this happens. We're just defining small f to be like this. Writing that F is invariant by SL to Z, we see that F satisfies the identity this for all G in SL to Z. This is what defines F to be a modular form by definition. Conversely, if F verifies the previous equation, we define capital F to be this, which is of weight k. So this gives a lattice function. So certain lattice functions give modular forms, and modular forms would be modular functions which are holomorphic at cusps. So we just define modular functions here, and modular functions would give me lattice functions of weight 2k. Right. Moving on, we define a subgroup gamma naught of n. This is like subgroup gamma naught of n. This is a subgroup of gamma n, which consists of matrices ABCD such that n divides C. Note that gamma n was just a A congruent to 1 and D congruent to 1. And these congruent to 0, right? Wait. Gamma naught of n is no, not gamma naught of n. Sorry. This would be SL to Z. My bad. So, yeah. This will not be equal to gamma naught of n. Like gamma n would be in this, but not the other way around. And now we define G2n to be the difference of this. Then we can show that G2n would be a modular form with the group being gamma naught of n. Like for all matrices in gamma naught of n, we have that AZ plus B by CZ plus D is equal to CZ plus D to the power KF Z. But this will happen only for matrices in gamma naught of n. Yeah, so theorem whose proofs follows from Fourier series expansion and so on. Basically, we saw that the Eisenstein series EK would kind of have some term omega n thing over here where summation n goes from 0 to infinity or something. This omega n, when written differently, will give me these things. D divides n such that D is not even, D divides n such that D is not 4z, not in 4z, and so on. This is just by simple calculation. The things that the fact that these are linearly independent can also be proved in a more involved argument, but it is still quite easy. And this spans nk of z not 4. This is tricky, but it's still a long and computational proof, so I've skipped that here. Right. Oh, and also this group is generated by these elements. That is also easy. It's similar to how you prove that gamma 1 is generated by. Right. So we define what is known as a theta function, better known as Jacobi theta function. Gamma be a lattice, and Q, capital Q, be a quadratic form, this thing, which is positive definite. Like for functions of this sort are said to be quadratic forms, and if the matrix this is positive definite, we say that the quadratic form is positive definite. Then the theta function of the lattice with quadratic form Q is this. For the particular case of gamma is just z, and if we take qx is equal to 2x squared, then we have this. This is particularly important in seeing that here there's a z, right? So when we try to take the modulus values of terms over here, we would see that to some extent, just considering the real parts would be sufficient. And so in all most of the proofs regarding these, this series will actually help a lot in the computations. Like all the facts of this will actually boil down to facts of this function. Right. Also define theta z k to be this. These are absolutely convergent. Theorem without proof again. This be the Fourier expansion. Then the coefficients satisfy the number of ways in which n can be written as the squares of entries of this vector v. This is also again by just simply calculations and taking note of the terms. It can also be verified that theta z4 is just minus 1 by pi squared g24 z. And now these g are quite, I mean, as I said, it's just some constant times ek, like E2 here. And that constant may vary, but it's just some constant that depends on this 2 over here. So it will be fine. As and when you do the computations, you'll see that these are all right. Right. Now coming to the four-square theorem, with all the work we have done, like we have not done, but I've just stated that you can take this as a result because it's just computations. Then for n greater than or equal to 1, there are these many ways to write n as a sum of four squares. I think we have all done in elementary number theory that any n can be written as a sum, any positive, like non-negative integer can be written as a sum of four squares. But this proves how many ways can it be written as a sum of four squares. So with the discussion before this, and also the form for G24 in terms of these things over here, we get that this happens. We have proved that the Fourier coefficients satisfy this. For this over here, just plug in k is equal to 4. Right. So comparing coefficients, this is say then we have this, like n is equal to 1 to infinity. Right. So yeah. References are these. First course in arithmetic, automorphic forms and representations. This is kind of the book that I'm principally following, but yeah, this does not have too much of definitions motivating what modular forms are, so I refer to this for that. And Keith Conrad's notes are wonderful, like for any topic that you want to read, algebraic stuff. Right. So yeah, I'm done.
Thank you for the talk, Ruchira. Does anybody have any questions?
Can you read the questions on the chat for me? If there are any questions in the chat.
There are no questions in the chat.
Okay.
Okay, so if there are no questions, then in that case, I would like to thank everyone for attending this talk. Everyone is requested to join the next talk on the invitation to several complex variables by Professor Shubham Sharma, which will be held at 2 p.m. Indian Standard Time today. Have a good day, everyone.